Tonight we're going to talk about Python for embedded development. Full disclosure up front, I'm not an embedded developer. Very much in the enthusiast realm. It's something that I find super interesting. I think a lot of times today, just due to the nature of the problems that we're solving in our day jobs and some of the focus on business areas and such, it's actually pretty easy to be programming without maybe thinking about some of the hardware level components. And so it's just an interesting and enjoyable thing to do. So if you have questions, please jump in, ask them. You said you were here from Atlas, so you know way more about this than I do. And I'm sure many others in here have more embedded experience. So, all right. So we're going to go ahead and get this out of the way. Anytime you talk about what is an embedded system, it's almost similar to asking where people draw the line between an IDE and a text editor, for instance. Everybody's going to have a different definition. For tonight, we're going to be focusing on system-on-a-chip type embedded systems. So what that means is there's more than just a microprocessor present. These are chips that have a processor, memory, and quite probably other sensors available on the chip itself. However, for the sake of completeness, Python also it runs on microcontrollers, systems on chip, various embedded definitions. Microcontroller is going to be a single chip. I've got some in the back if you want to check them out when we're done. These contain non-volatile memory, volatile memory, clock, and some other components. Typically not any type of external sensors that you might find on systems on chip. So systems on chip, these are going to include some type of CPU, potentially a GPU type component, caches, different types of things. These can range from something like the Circuit Playground Express to maybe you might consider the Pi Zero or the recent NVIDIA Jetsons to fit into this category. So why would we want to use Python for embedded development and learning? And honestly, the reason for Python in the embedded space is the reason for Python in a lot of other spaces. It's going to typically offer a relative increase in the speed of development and prototyping. So as an enthusiast or somebody that maybe doesn't have a rich background in this space, I'm not necessarily from the get-go having to understand the variety of buffers and data sheets, compiler flags, and such that I would writing my own C or C++ code against a chip. But Python does have a rich ecosystem around C and C++ bindings. So if you are doing something in Python and you need to use a snippet of C or talk with C or something like that, that's actually pretty easy to accomplish. CircuitPython, which we'll talk about for the majority of the evening, also offers up a REPL. So if you've been using Python for a little while, I'm going to just go ahead and show this here. You know that, or you may know, that if you go to a command line or a terminal and type in Python or Python 3, you'll get what's called the REPL. And it's an interactive environment where you can write code and get an immediate response. And it just creates a real fast feedback loop for checking logic, prototyping, maybe testing, calling a function, and things of that nature. CircuitPython and MicroPython also have a fairly rich standard library out of the box, similar to Python, but by no means as expansive just because of the constraints of working in an embedded space. The ecosystem is getting more and more rich. So Python itself, if you go out on pip, you can find a package to accomplish many things. Some people were commenting on it earlier about, you go online, you find a snippet of code, and a lot of times you can find the problem already solved for you in Python. And so similarly, Python has a growing ecosystem in this space, a growing set of packages and a fairly rich community that's developing. And then the tooling around that's just getting better and better. There are commercial entities investing in Python being part of their data sheets and offerings and whatnot. So the tooling's actually coming along pretty well. While this is focused on why Python, why not would be a lot of the similar reasons why you would use Python on another project. So for instance, if you're on an embedded system that's, for instance, an FPGA or something, doesn't make sense. If somebody's offering that C library and you just have a space constraint that can't be met with Python, similarly, a lot of the reasons you would come across. So Python on embedded, I could find some papers, people writing kind of graduate PhD thesis statements on this about 15 years ago. It's not an entirely new idea. However, I think MicroPython kind of created a big splash around this. So MicroPython was kickstarted in 2015 by Damien George to basically create the Pi board and MicroPython as well as some interaction with the microbit. And one of the things that MicroPython did was implement UPy. UPy is the actual interpreter that runs on the embedded chip. So if you've been using Python and you have some experience with other languages, you'll know some languages are compiled ahead of time. So you write your code, that code goes through a compilation step where it's translated into machine code, and then that machine code gets executed. Python is interpreted, which means that you write your Python code. There's not a ahead of time compilation step, and this is kind of glossing over details, but for the sake of basically you call the Python interpreter and tell it where your code's at. The interpreter is then going to start taking that and taking the bytecode and turning that into machine code. And so UPy is that interpreter taking bytecode, translating it into machine code for the embedded space. And so MicroPython created that. There's been other projects. Here in a moment we'll be talking about CircuitPython that make use of UPy. There's other forks of it. And there's even, I'm not highlighting it here, but a company called Xarin that actually has a full commercial offering around Python in the embedded space. I think they've got the interpreter down to, I want to say it's something like 25 kilobytes, so pretty small. But the thing I want to highlight here is if you didn't know that you were looking at code meant for MicroPython, this looks like regular Python code. So when you're writing Python on an embedded system, yes, you're going to have to be thinking about the fact that you're working on an embedded system, but you're not learning a whole new language. If you already know Python, then similar constructs that you're used to using in your other code is going to be found here as well. So a fork, CircuitPython, which is what I'm going to focus on tonight, is a fork of MicroPython with the explicit goal of being beginner friendly. So MicroPython, kind of in a lot of ways, it surfaces details of the hardware as you begin to do more and more work that you may or may not be interested in. So it does try to reflect in the language things like registers and allocators that maybe typically using Python you're not as interested in, or interested might not even be the right word, but you might not be attempting to go that low. And so MicroPython surfaces a lot of those things, makes them very explicit. CircuitPython, focusing on the beginner-friendly component, has worked to unify what's called a machine API and kind of abstract your code from the actual board that it's running on. And so this is a similar example. You'll see import board on that one, PYB there, but CircuitPython does in the background basically detect the board that you're running on and does a lot of the mapping of pinouts and things for you automatically. All right, so any questions there?
So to be clear, the CircuitPython helps you abstract away the hardware level?
Yes.
So you might write once and it might run on different hardwares?
Yeah, and so the main thing that you'll run into there is depending on which board you're switching between, you're going to have different amounts of memory. The code itself would be the same, it's just making sure that any extra modules can fit into the memory space. And we'll kind of look at that too. But yeah, that is kind of one of the goals.
There's also one more board there, micro beach, right?
Micro what?
Micro beach, BIT. That's kind of popular today from England.
Okay, yeah. There's, like I said, there's, if you Google like embedded Python, there's a Python wiki page about it. There's multiple forks of it. These appear to be the two kind of, I don't even want to say the most active, but maybe with the breadth of ecosystem around them and the breadth of users where you're going to get active mailing lists and forums and things of that nature. Okay, so kind of mentioned that one of the goals of CircuitPython was making it easy to get started. So kind of personally for me, this, I guess it was not this year, but last year I was at PyCon and Adafruit was partnered with Microsoft giving away some boards and offerings. And one of those was the Circuit Playground Express, which is meant to be a relatively easy to use introductory chip with LEDs, a speaker, multiple different pieces on it. And so one of the things that's nice about the Express chips from Adafruit is whenever you plug them in, pull this up. The Express chips are preloaded with a UF2 bootloader. So what that means is you can interact with it like a mass storage device. So if you're used to plugging in a USB, it works exactly like that. Well, similar to that. I do call out that works for the Express chips because Adafruit has a pretty wide variety of CircuitPython boards. The non-Express boards, you will actually have to like flash a bootloader onto them. And if you run into that, we can talk about it. But the Express chips, you load them up and you can drag and drop files. So let's just do this. You can drag and drop files, or you can actually, if you can type, CD into it, and then you could actually begin manipulating files here. So from the get-go, very easy to talk to. It's a USB plug-in. One thing, you'll see this throughout the docs, is make sure you're using a USB data cable. So there are USB cables that are power only, and if you use one of those, it's not going to show up as a USB device, and that's a lot of fun, and you'll be beating your head against the wall trying to figure out why.
Does this come from personal experience?
Yes, it does. So I bring all of that up because when you first go to get started, the Express devices are going to come with CircuitPython preloaded, but CircuitPython is, as I said, very active. In fact, 3 hours ago, 4.0.2 came out. And I guess, yeah, let's see if we can scroll down far enough. By the way, that's how many boards there are. What's up?
Is this a community-only forum? Does it have some sort of business behind it, maybe?
Adafruit.
Okay.
There's many other SparkPython, or Adafruit runs MicroPython, but
Adafruit runs CircuitPython.
Okay.
Damian George runs MicroPython.
well, you can buy this stuff. I mean,
Yeah.
you know, that little thing you have is like $5.
Yep.
You can buy. You talked about an SOC, a little tiny 4mm by 4mm chip has, you know, the processor and Wi-Fi and Bluetooth and all that other stuff. So you can, you know, those things are pretty cool because you can operate them, you know, on the distance.
Yeah, we'll get into that here in a bit, because it is staggering the amount of chips available for CircuitPython compatibility, and if you have an idea, chances are there's a chip that will help you make it happen. That's one of the things that's really fun about this. And as far as, so you can actually see up here on GitHub that the CircuitPython is maintained under Adafruit. If you're familiar with Adafruit, they do a lot of stuff, but they have a focus on education and getting people into kind of this embedded space. So, like I said, there's new releases coming all the time. One of the things that's cool is, so far, we've hooked up, not a lot super interesting happening. We have a green LED, we can see it as a USB, right? However, let's update the firmware, let's update the firmware. So, as I mentioned earlier, it's got a bootloader already on it. That's why we can see it up here as USB. CircuitPython itself is the actual firmware. And so, I have this downloaded. Sorry, I skipped this because I have it downloaded and I don't trust the Wi-Fi here. So, if you go to circuitpython.org, this is something Adafruit set up recently. You can go to the GitHub release pages, and there's all of these releases and the release notes, and I definitely recommend you checking it out. But they also have circuitpython.org, where you can go and search for whichever board you're using. And you would click on that, and it would actually take you to the download page for the firmware for that device. And so some of these will have a .bin if you're not using an Express chip. For the Express chips, they have the .uf2, so you'll get the bootloader and the firmware. If it's a .bin, again, you have to go the route of using a tool, for instance, like BOSIC, to flash that firmware onto the chip itself. It's a bit more involved, but not too bad once you figure it out. So I've got this downloaded, and I can attempt to drag it. Yep.
Do you have to use a custom flashing tool, or is it enough to like just DB it to the?
For like the firmware, if it's a .bin.
Yeah.
I don't know. Documentation is pointing towards using BOSIC and flashing it, because otherwise there's nothing there yet. It's just kind of like a chip sitting there waiting. So, yeah. And so, gonna reset. So a double tap reset, you'll see that this has gone into C-Play boot. We can see the UF2 there. We put the bootloader on it, along with the firmware. And interestingly enough, you'll also see that it returns the name that it had, as well as my files. And the reason for that is the firmware is actually flashed to a separate area of memory on the Express boards from where you're actually storing your work. That's nice because if you brick a device or if you do something really crazy and you need to reset it, it doesn't wipe all of the non-volatile memory. It just overwrites where the firmware is at. So use version control, back up your files, but if something goes sideways, especially on these boards, you haven't necessarily lost all of your work. Okay. Any questions about that so far? All right, so continuing on, you can connect to these in a variety of ways. So if you're getting started, Adafruit recommends using the Mu editor. The Mu editor is a Python community effort, and basically it's got some built-in niceties around serial ports. So definitely check that out if you're new and it fits into your workflow. If not, and you're on some type of POSIX-based system, you can make use of screen. And so when you plug a device in, if you look under dev, you'll see a variety of TTY devices. You can filter this with grep or something if you wanted, so we'll do that. And we're looking for USB, and I did that wrong. Yeah, I'm screwing it up. Anyways, so you'll see up here this TTY.USB modem. So what we can do is screen into that. And by default, the boards are talking on baud 19200. You can also get them to a 115200. And so this is actually on the board now. So we can reload we can reload the code if we hit Control D, and it'll actually start running main.py or code.py. You'll see those there. We can also interrupt that and hit any key. And what we do is we're into a REPL now. And so we can begin. I'm sorry?
Can you make the text bigger?
I can try. Actually, let me do this in iTerm. I know I can do it there better. Oh, yeah. I need to release that. Thanks, Colin. Good news is, just unplug it and plug it back in. Have you tried turning it off and on again? All right, and now we're back. So inside the REPL, this is going to be similar to your normal REPL experience. So we talked about board earlier. So if you call dir on board, this is actually the pinout and sensor information for this specific board. This board is actually going to be different for whatever you're interacting with. And calling dir on that, you can begin to learn about what's available if you're not looking at the pinout sheet. So we could even do dir or dot and learn some more if we want. Let's see, I'm trying to think. So it's a REPL. We'll look at something a little bit more interesting here in a bit, but that was just kind of mentioned as one of the highlights. All right, so far we've talked about, let me go to this real quick because Yukai, you had mentioned this. So this is flashing with BOSAC for .bin rather than UF2, and it actually goes through that. The primary thing, if it's not an express board, you're going to have to do this. And as far as like just beating onto it or something, you can definitely attempt it. I don't know why it wouldn't work. The main thing is just that you get it into the right location. And so BOSAC's going to take care of that based on the offsets that you provide. Because the boards are going to be looking at a specific memory address whenever they load up. So you could probably do that.
Does that mean that the memory segmentation you were talking about earlier, are those like two separate memory devices?
Every
Or-
board's different.
They're different boards?
Yeah.
Oh, so different boards that do a different thing?
Right.
Okay.
Yeah. And that's actually kind of reflected if you'll see down here, for instance, like the M0 boards and the M4 boards, even if you're going just this route, not even talking about that, have different allocator areas or offsets because of the different bootloader sizes. And so some of the boards are also going to have a contiguous memory device, and then some of them might have multiple memory devices. So.
I don't know enough about DB to know if it does offsets like that.
Yeah.
So maybe that's why, but the special utility is specifically needed.
Yep. So the nice part is, so this is the Welcome to Circuit Python introduction. You'll see they cover Windows, they cover Mac, they cover Linux. Adafruit's a learning company, an education around software and hardware company, and so they tend to try to show this for all the platforms, for the various chips. Each chip has its own walkthrough. So recently I've been interacting with the Feather device, and so you'll see like this page has a similar walkthrough, assembling the board, antenna options, things like that. It's unfortunate that this is not loading right now. Okay, here we go. All the boards, Adafruit also puts out some really nice pinout diagrams that are available, if it'll load. And one of the things to notice with them is the boards are Arduino and CircuitPython compatible, as well as a lot of times you could run MicroPython on them if you want to. And so even on the pinouts, they actually provide hardware level pinout information. So you'll see kind of a legend talking about what the different colors mean. So like port pin, physical pin, IDE. And so IDE is referring to CircuitPython versus Arduino. And so on the various pins, it tells you how to refer to those in CircuitPython or how to refer to them in Arduino. Gives you the physical pins, the port pins, kind of everything you need to know about communicating with this device. So that's kind of getting started with it. You can go through, check out the tutorials. I pretty much wanted to work up through the REPL and just show that because it's really nice. You can plug a board in, you can see the board, get the firmware on it, boot up a REPL, and immediately you can begin playing noises through the speaker. You can begin turning on LEDs, changing colors of LEDs, turning them on and off. And I'll kind of talk about, I've got a demonstration here in a bit. I used the REPL a lot when I was trying to figure out some things about how to get CircuitPython to operate my home Roomba. All right, so Zoom. One of the other things I want to call out is that similar to Python, CircuitPython has the concept of built-ins. And so I said that, and then I don't know where my page went. Here we go. All right. All right, so CircuitPython built-ins. This is relatively small when you compare it to Python itself, but you've pretty much got everything here that you really need to begin working. So you've got your flow control statements that you're going to be used to. Math is available by default just because within the kind of embedded space, and I'm not sure, like nobody's told me this, but I would imagine because people are trying to pull a lot of sensor data, it's nice just to have math built in off the bat there. You have tuples, lists, arrays, and dictionaries. One thing that I'm not wholly sure of is why sets aren't there. Maybe it's just not that common in the space, but those are the built-in collections you have from the get-go. Classes, objects, and functions, as well as lambdas. And what's really nice, and Randy touched on this earlier, and I'll show this a little bit here in a bit, is since you have classes and objects, you also have the object model from Python. So you have a lot of the dunder methods available to you, which means that you can use context managers in this embedded space, where cleaning up after yourself, especially on error or exceptions, can be super useful. And then as far as the core modules, so Python by default ships with a very large standard library. CircuitPython, however, ships with the built-ins, and then there's a CircuitPython bundle. And so you can download that from the circuitpython.org site, or go to GitHub and get the latest from there. And you'll see if you open up, this is the bundle. It covers a lot of ground. You've got various boards, you've got Bluetooth tools, you've got radio tools, sound. I see Azure in there, AVR programming, fingerprint, all kinds of stuff, GPS detection. It is massive. And the way this works is instead of all of that automatically shipping in the CircuitPython interpreter, because again, we're in a kind of a restricted embedded space, these modules live in a folder called lib. And so this is a listing of all the modules, similar to other Python package documents. If you want to make use of something, for instance, a supervisor, if you had internet that was working, you could go to that and check it out. Earlier, when we were looking at the CircuitPython device, you'll either have a lib folder present or you can create one. And this is where you put your modules. So when CircuitPython starts running on the device, it looks for code.txt, then code.py, then main.txt, and then main.py in that order. And whichever one of those it finds is what it begins executing. And so from those files, you can do imports, and as long as the import is a built-in or within the lib, it'll pick it up and import it as you would expect it to. So modules are relatively straightforward in the sense of download it, take it, drag and drop. Let's just pick one. Drag and drop that onto the onto your CircuitPython device, and then from there, just make sure it's in lib, and you can import it. The main thing to keep in mind is typically the modules are going to be interacting with various pinouts, and so just make sure, like, if you're trying to interact with a Bluetooth sensor and send data to a given pin, that your board actually has a Bluetooth sensor.
You said this. You called this Roomba Pi, and you said you have Roomba at home. Are you making one, or is this actually interacting with Roomba? Or oh, I see.
I'll get to it. Now that is so. One of the things is if you've got a lot of devices, then keeping up with what they are when you plug and unplug can kind of get to be a pain. And so, for instance, I could rename this DerbyPy, and that'll actually write to a file on the device for its name, and that way when you plug it in, instead of just showing up. So when you're in a bootload mode, or like a reset mode, so you can see the LEDs on there, and so you'll see like this is ready to have the firmware flashed right now. So I double click this reset button, and you'll see it also changed to C plate boot. And earlier that was when I go and put the firmware on it. You'll see it turns off and then comes back, and that again gets into where the firmware is being written to a specific memory location. It knows to detect it from there. Our files have been written to a separate memory locations. That's why we see them there. And because the firmware also knows to make this device get the name from the file, now it's back to being that DerbyPy device. So that's a lot of kind of just the beginning to get started with it, how you would take a device, actually get something on there, and then the REPL kind of shows how you can begin to interact with that. Again, these mount like a device, and so once you have it with the CircuitPython firmware, you can actually CD into it and treat it like a device on your system. And so, for instance, this is what's in main.py. You'll see where I'm importing the board, digital I/O, which is for interacting with the various pinouts here, bus I/O, and time. And then I've got hex codes. So that's another nice thing. Python has pretty good support for going between bytes and strings and hex and octal and all these different formats you might want, and making it relatively painless. And that's part of CircuitPython as well. So here I've got strings. I've indicated they're bytes, and these are in a hex format. And I've created a list of them. I've then set a couple of pins for output information. I've set the baud rate on a UART. The Roomba has a specific command sequence to wake it up. And then you'll see in here where I run a specific sequence of commands to start it. I sleep for 2 seconds, then I stop it and just kind of do this in a couple cycles. And so this actually started out with me just in the REPL, writing through and working through this and seeing, because that's something handy too. MicroPython does this, but I think CircuitPython makes it a little bit more handy. Is earlier you saw like these hex codes being printed out. Whenever you call print in CircuitPython, it automatically writes that to your serial output. And so if you have this hooked up to screen or something like that, you can use this for debugging. Like you can actually see, is this like the right hex code, or like, am I writing to the UART what I think I'm writing to the UART? Especially, you're potentially in a constrained space where you don't want to be writing that to a file and filling up memory, trying to figure that out. So that was very useful to me personally. And since it is a device like that, you can be in PyCharm, Vim, VS Code, a variety of editors, and actually editing your code, and it'll write that out straight to the device. And it actually has a reset sequence, so if you're not in the REPL, if you're not in the REPL, anytime you save and overwrite a file, it actually goes ahead and resets, goes through that sequence, looking at code.txt, py, whatever, looking for which one has your code, and begins executing that so that you're not having to sit there and go through a reset sequence manually. Trying to think if there's any other. So, any questions about that?
So that's the CircuitPython firmware.
Yep.
That's doing all of that code reloading, looking for the code, making all this kind of easy.
Mm-hmm.
Okay.
Yep, and it includes the interpreter. Yep.
You can think about it as a compiler engine, a dynamic engine.
Yeah.
To translate your code to the binary code.
Yep.
You might touch on this a little bit later. You had mentioned something about sensors and inputs and reading and writing. How do you handle data coming from a bunch of different places, like asynchronous handling of that sensor information?
Yeah, so it depends. And so if you have a lot of asynchronous type code that you're trying to run on an embedded device, you're probably going to want to look at MicroPython. You might start out kind of synchronously prototyping in CircuitPython to get the speed of like feedback there. But then once you're ready to actually make that concurrent, MicroPython is 3.5 compatible, which is where the async and await keywords were added.
Okay.
And MicroPython actually supports async I/O.
Okay.
At this stage, there are GitHub issues open around it. I actually have them in a tab somewhere in here because I was looking at this recently. Yeah. MicroPython or CircuitPython doesn't support asynchronous code real well right now. And part of that's because the initial focus for CircuitPython was kind of that learning and beginning, and now they're beginning to expand beyond that. And so there is async I/O in MicroPython. There's some limited support in CircuitPython if you get creative, but it's not full-fledged.
I was going to say, I thought there was a library for that, but I keep thinking using a Raspberry Pi instead, which is like a full-out computer.
Yeah, so there's Blinka, which is CircuitPython for the Raspberry Pi that you could use if you're wanting to interact with the GPIO pins on the Raspberry Pi. You could use that if you want, also depending on what you're doing. It's a Raspberry Pi at this stage. I mean, the 4 has 4 gigs of RAM, and you could just start running the core Python interpreter.
So do you use like GPIO library and a machine and some of those?
You can.
Yeah,
Well,
but
like MicroPython has the machine library. CircuitPython kind of abstracted that away.
Okay.
So, yeah.
And that's how you can operate your pins too,
Mhm.
your microcontrollers.
Yeah, so like there's the motor module if you want to like interact with a module. There's GPIO module. There's UART that we saw up there, depending on if you're just trying to read right from a pin itself. Kind of depends on what sensor, but the sensor probably has a library if it's not just a digital in out. Okay. So kind of what got me to go down this rabbit hole was last year I was at PyCon, and as I mentioned, Microsoft was giving away the Playground Express kits, and so I ended up with a couple of these boards, some alligator clips and different things, and I didn't really know what to do until at work I worked with an individual at Humana who talked about, if Todd Howard is ever here, ask him about his Roombas. He'll go on about them. It's a lot of fun. But he's driving those with Raspberry Pis, and I was like, there has to be something smaller and more compact for that. And I started to look at this, and iRobot actually has a connector on all of their devices that's called the Open Interface. And the Open Interface actually contains a full spec for how to talk to the Roomba. And so it has a mini DIN port on top. You can kind of see how to talk to it. So it's got a baud rate port, pin, receive pin, a transmit pin, grounds, and power. And if you go through reading this doc, it basically tells you how to turn it on, how to get it started, the sequence of events that have to happen at startup, the modes it can be in, and then all the commands that you can run. All the way down to, you could actually make it play songs if you want to, because it actually has like a full note chart in here somewhere. Like, this is the code for A sharp, and this is the code for B flat. Yeah, right there. And it also includes, it includes all the instructions for the wheels, so you can control how it's turning. I mean, like, it is open and available for you to look at. And so I started to get interested in this. As I mentioned, I have no background in embedded devices. I've been on the software side pretty much my whole life, and so this started to get really interesting to me. And so if this kit came with some alligator clips, and it'll be easier to show you later, but basically alligator clips, instead of soldering or other techniques that you may not be comfortable with, or having to hook up a breadboard or different things, alligator clips kind of look like jumper cables, and you can put them on various pins, and then you can connect them to a pinout. So I started getting curious and started to read. I referenced the Circuit Playground Express pinout chart and figured out, okay, here's the transmit pin. I have to have this thing grounded, and I need to be able to send a baud rate code to the Roomba to get things rolling. And so hooked up the 3 pins, and the Roomba wouldn't respond. And come to find out, there's actually a bug in the firmware that iRobot will send you a handy little dongle for to update, but it doesn't listen when it's in a certain deep sleep mode without that. So after figuring that out, I basically spent time in the REPL playing with all this, and I'm currently working on a library called Circuit Roomba that is meant for use with CircuitPython devices, and it exposes an API for interacting with your Roomba. And so the idea being you initialize an interface with the Roomba itself, and then the rest of the commands are basically just simple function calls: start, safe, clean, stop, power. Plan on adding all the drive commands later. What gets fun though is every board has different memory footprints. This works really well on the Circuit Playground Express, but not the Feathers. And so that's something to kind of keep in mind is while CircuitPython itself is board agnostic and can move between boards with the same built-ins, because the different boards are going to have different memory capacities and different things, depending on how large of a board you prototype on versus the board you attempt to move to, your code may be too big for that. So I'm actually working on a stripped down version of this, which is what I have running on the current device. So has anybody in here heard about LoRa?
Heard about what?
LoRa, L-O-R-A. It's a low power radio. Huh?
Sensing distance?
It's for sending radio. Yep. So one of the things, so as you begin to talk about sensors, you need to think about how far you're attempting to send information, how you want to transmit that. So does it need to be secure? Can it just be transmitted? And that comes up because you have different things like Bluetooth Low Energy, you have Wi-Fi, you also have things like LoRa and regular radio. And I bring that up because Wi-Fi can get kind of annoying at times, especially if you're attempting to do embedded, because now not only do you have two devices trying to talk to each other, you have an entire TCP/IP stack, potentially some type of network stack. You also have a router in the mix somewhere and other components. And so you suddenly have taken worrying about two devices talking to each other and added a ton of middleware to it that could or may or may not work, may be flaky, gets kind of interesting. And so if you're going to be transmitting just kind of between boards, which is my goal here, you have things like LoRa and Bluetooth. Now, again, with Bluetooth, the thing that gets interesting is the discoverability component. And so, okay, I've got two devices, I want them to talk to each other, how do they handshake? So if you're doing secure stuff, that matters. But depending on what you're doing, like turning a Roomba on, you may or may not care. By all means, if one of you want to war drive my house and turn my Roomba on, I welcome it. I will find it hilarious. But so with that, and I bring all this up because I was kind of thinking about it, because my end goal is to be able to send a text message to start my Roomba, because I leave the house and I forget, and then I'm like, man, I could run this while I'm not home, and I just want to do that. So started looking, and Adafruit had these feather boards. You can check it out after. It's about this big, that wide, pretty small, low profile. And it's nice because I can put that on the Roomba without worrying about it sticking out, getting ripped off or something as this thing rolls around the house bumping into stuff. And then the other cool part is there's a LoRa bonnet for the Raspberry Pi Zero. And so the nice part here is if I want, I have a Pi, so I have the ability to have Linux or Raspbian on this. I can hook it up to a network if I want because it has Wi-Fi out of the box, but the LoRa bonnet suddenly allows me to just talk over LoRa. So I have a LoRa board attached, or just say a radio board attached to the Roomba. Another thing, be very careful what power sources you plug stuff into, even though it'll regulate, like the CircuitPython boards all will attempt to regulate 5 volts down to 3 from a USB device. I blew a board up this morning, did something I can't figure it out. So some power devices, just make sure you got a legitimate power device. The other thing is some of these power off if you don't pull enough. So I'm going to get a lithium battery pack because I have to have both of these plugged into the same power supply for them to draw enough for it not to shut off. So that was a fun thing to figure out too. But so anyways, on the bonnet, this is a pretty neat little device that Adafruit sells. So it adds radio to a Raspberry Pi Zero. You just plug it into the pinouts. And then it's also got a handy little LED screen. And so I set this up to where I could tell it to send various start commands and whatnot. And so basically, the Roomba can be sitting there ready to roll. Actually, it's for cleaning. And I can also send the stop command with a button. And so what makes this fun to me, I don't have embedded experience, but I'm now programming my Roomba. I'm able to interact with that. I'm able to kind of bypass a lot of tool chain that I want to learn eventually, but kind of getting the feedback loop to kind of keep going, keep learning this has been really helpful because I already know Python. I know how Python works and a lot of things. So it lets me worry about that. Learning about the electronics, the power component, the UART, the serial, these different things that I don't know instead of trying to learn a whole tool chain while I learn anything about electronics itself. So it's really, really handy in that way. And then I realized that I accidentally, so one of the other things is, so now I can transmit to this over LoRa with the button push, which is really neat. I've basically got a Roomba remote now. But because it's a Raspberry Pi Zero, I can also have this monitor Twilio endpoint and just send a text message, and this already knows the commands to send to start it and Roomba started. And because it's on Wi-Fi, I'm going to, the Roomba will actually output data and all these different things. And so I'm going to stream data from my Roomba into an Elastic cluster and have fun like seeing what I can learn about its run paths with that. And kind of all of this leads into a whole other project where now I've got radio working, I've got Python, I've kind of got this prototype, I've got a communication channel. And so there's also, as I mentioned, if you can think of it, there's probably a sensor for it. And so there's moisture sensors, and this year I built a couple of raised bed gardens, so I'm actually going to put some moisture sensors out there, put feathers on it, transmit radio back to the Pi, have the Pi write to an Elastic cluster and send me an alert whenever the soil moisture level is too low, and then I can only water my garden when I have to and be lazy the rest of the time. So that's some fun you can have with Python on embedded devices. I personally enjoy it because working on software, there's a lot of things that I really enjoy. A lot of projects I've had the opportunity to work on that have been really neat, but one of the things about the embedded devices that I've enjoyed is it's a physical good that I'm interacting with. It's right here in my world. It's not just in a screen, and I find that super interesting personally. So I'm not going to go through all these last slides, but if you kind of want to know some further ins and outs, this will be up there talking about what a bootloader, firmware, boot sequence, and different things are. PC Mag apparently has an amazing definition encyclopedia, by the way. Did not know that. I was Googling some of this, so that's linked there. So if any of this was interesting to you, I wanted to share a couple of resources. So Adafruit's website is really awesome. They have a very active forum. They also have a Discord server set up where Dan Holbert, Tanit, and the actual head of the CircuitPython interpreter, Lady Ada or Lemur Freed, all of them are in there. They're chatting. They're helpful. It's a very, I'm trying to think, it's a very welcoming community because I've asked some very stupid questions in public on that Discord channel and gotten helpful answers instead of ridicule, so that's been really nice. Hackaday is a really cool site if you're familiar with it. They're actually running a connected device contest right now, so check that out if you get a chance. Embedded is a really interesting podcast if you enjoy listening to podcasts, and they have blog posts that are really helpful. They have a Embedded 101 series, and Embedded Artistry is another one. I've got some books linked here. Highly recommend those. I've worked through the first two, and I'm working on the third one, and then some additional resources if you're interested. Specifically, the Adafruit Discord channel, call that out, and Hackaday.io is a very interesting place to look at. And then lastly, MicroPython. So Damien George had worked with CERN in other areas, and the EU has actually done different funding grants for MicroPython at different times. And so one of the interesting things to come out of that was actually using MicroPython on CubeSats. So it really does span the range of beginner hobbyist learning all the way to very production, high-end products and workloads. Any questions? Or if you end up working on something, I'd love to hear about it. This has been a lot of fun for me personally, and so I think you'll enjoy it. Also, I've ran into the weird edge cases, or I've ran into missing something in the dock. So for instance, plugging in a non-express device and wondering why it didn't show up as a USB mass storage device like the express boards do, and figuring out how to flash that firmware, some odd power things here and there. So if you work on something and you want to talk about, by all means, post in the Python Louisville channel on Slack, reach out to me, let me know, and good luck.
Very good.